So what I used was called a colorimeter. And basically, here, let's back up. You know, our eye can only see Roy G. Biv, right? Everyone know what Roy G. Biv stands for? And then in art, I guess, what was that? It's a color wheel. Remember the color wheel? And so red, and then orange, then yellow, then green, and then blue, and then I guess purple or violet. So this is kind of the color wheel. Yes.
You intentionally forget to drop the EM line.
I just get so excited, I hop on to the next one. So, and then what is it called when they're directly opposite each other? What? Complementary colors, complementary colors. Okay, so, now the human eye, when I say can see Roy G. Biv, it sees from about 700 nanometers, and that's wavelengths of light, to 400 nanometers or wavelengths of light. So it's a small amount. And if we were to start it up here, so violet goes from like 400, it's only to 450 nanometers of light. And then blue is like 450 to 480. It's a little smaller. The blue area is a little smaller, but green's one of the bigger areas. So it goes from like 480, it's like 80 big. So that's 560 to 560. And then yellow is 560, and that's a small one, to 600. Orange is a small one too. So orange is 600 to 640. And then red is our 640 to 700. Those are just nanometer wavelengths of light, right? They're not all equal. See how some are smaller and some are bigger. So when you look at the rainbow, that when you shade in the green is larger than the other colors. It just takes up more of the rainbow. Yeah? You guys know the rainbow? No? Roy G. Biv? You ever seen a double rainbow? Yeah, those are cool. The whole thing, have you seen the whole rainbow? Yeah, and you saw the whole rainbow. That's kind of super cool. Instead of just a piece of it, it actually goes. You gotta kind of be at the coast or somewhere. See that? Okay, I digress. So the colorimeter, we put our sample in the cuvette, and the colorimeter has a light source. And that light source, right after that light source, basically that light can send any wavelength of light we tell it through the sample, okay? And if the sample is red, like ours was red, if the sample is red and I shine red light on something that is red, I shine red light. You guys know how the eye works? So that chair is blue right now because it's absorbing yellow and it's absorbing red and it's absorbing green. It's reflecting back blue. And that's what my eye sees, right? So if I shine red light on something that is red, is it gonna bounce it back? Right? It's gonna bounce it back. It's not gonna absorb it. So if your sample is red and you want to go transmittance, you want it to go through it, I shined a green wavelength of light through it. okay? Through our sample, I shined green, so it would go all the way through the sample. Now on this side is a sensor, and it's basically counting how much light hits it, how much light hits the sensor. So we can send any color we want through it. And basically the intensity of the light, I stands for intensity of the light. The intensity of the light going through the sample shouldn't change. And if it all goes through, that would be 100% transmittance. That's how light goes through, 100% transmittance. So the intensity at the beginning versus the intensity transmitted through it, we're comparing these two things to get it to be 100%. Basically, what was transmitted divided by the intensity it started with times 100 equals 100%, right? So this would have to be 1. It has to be the same number, like 2 over 2, 3 over 3. The intensity we start with is the same that comes out of there. Yes?
Is there sensors on like doing what color the actual sample is, just to make sure that it's the exact? Just getting a focus.
In the calorimetry, there is not a sample. There is another tool that you could go exactly what wavelength is coming off of that. But it's not part of the calorimeter. But that's yeah, that's getting really precise. Yeah. And actually right after this light, there's more to it, but this is the simplified version. So we did percent transmittance. Now, it was 100% for water, and then we had a red sample in here, and the higher the molarity went, the less was transmitted through. Well, if it wasn't transmitted through, a couple things could have happened to it. It could have, the light could have gone right into the sample and been absorbed, or it could have gone and bounced back. Does that make sense to you guys? Could have done two things. Could have been absorbed by it, so it's just kind of gaining light energy, or it could bounce back. So percent transmittance tells you how much makes it through, but it doesn't tell you how much is absorbed, but they are related. They are completely related. Does this make sense to you guys? Haven't lost anyone. So there is something called Beer's law. Beer's law. And it relates absorbance, A for absorbance. Because if we look at the color wheel, whatever's not transmitted is absorbed. So they're like complementary. Yes.
Is there a max amount that can be absorbed? Is that something that happens?
At a sample, a certain sample of matter can't absorb anything else.
Yeah.
Yeah,
So if it's a max amount of light energy, I guess.
that it can absorb. Absolutely. Why? Oh, okay. Absolutely, yep. So Beer's law states that absorbance is equal to, I'll just give you the numbers, but don't freak out. It's sigma BC, okay? And C is what we know and love as molarity or concentration. Molarity or concentration. B, this is kind of cool. This is the length the light has to travel through the sample. This is how far the light has to travel through the sample. Well, all the calorimeters and spectrophotometers I've ever used in my whole life, which is a lot, the length that they have to travel is 1 centimeter. So those little cuvettes were 1 centimeter, even if you use the round cuvettes, even if you use a spectrophotometer, it's 1 centimeter. So the length is 1 centimeter, which is very handy. So that's what B is. It's just the length the light has to travel. Now sigma here is called the molar. So we're dealing with moles. Absorbance, so absorptivity. Molar absorptivity. And it's going to vary based on what's in the cuvette, right? Molar absorptivity. That's absorbance. Now, why do we care about absorbance? Well, we'll get into that in like one day, but very easy to find transmittance, and the relationship between transmittance and absorbance is really kind of cool. Absorbance is equal to 2 minus the log of percent transmittance. Now you might feel like that's out of left field, but this is log base 10. And get this, if we were to take the log of 100%, what do you get? You can do it a log of 100.
Wait, for 100%, do you have to convert it to like
No. What's the log of 100?
1 or 2?
2. So what is 2 minus 2? 0, right? So when transmittance is 100%, it's all going through. Is anything being absorbed? No. So that's the relationship between the two. So, you know, it looks complicated, but it's not. It's just, they're just using the log base 10 to get you to that function. So, so you wouldn't go the log of of 1. You wouldn't go the log of 1. You go the log of 100. So you don't convert out of percentage for that, which is a very good question. So if we know our transmittance, which we can get our absorbance. Any transmittance we can plug into this formula and get our absorbance. Yes,
What units are absorbance measured in?
none. No units. No units. I mean, they're called absorbance, but there's no unit to it. So within a sample, we can tell how much goes through, how much bounces back. Are you all with me? Now, since this 1 centimeter, I were to rewrite this absorbance, this is a 1. Anything times 1 is just itself, right? So do I have to keep that B in there? No. So I could say it's sigma C, right? So I have something equals something times something else. I hate to do it to you guys, but doesn't that look a lot like y equals mx? Right, linear. So we can use linear regression on this. So get this. So if we graph this, and you graph percent transmittance, what if we do absorbance? Y, if our y is the A, M is going to be our slope, which we can get. C is our X, or concentration. So this is molarity versus absorbance. We get, one's high, the other's high. We get a direct linear relationship between these. Why do we care? Because those calorimeters are easy. Yes.
Does it matter what like solution you're using? Like if
No.
you understand molarity of
It-
like Kool-Aid or something else.
Yeah, it doesn't matter. Even when you make your copper 2 chloride solutions, this is how I'm going to grade you. I'm just going to pop it right into that calorimeter. So what makes this so great is any absorbance, you can have any liquid, measure the transmittance, boom, calculate the absorbance by doing 2 minus the log of transmittance. That absorbance, you go to the graph, you go over and you go down, boom, and you know the molarity. Yes,
Does this only apply for solutions?
yes.
It's all for gases.
It only applies for solutions.
Does my previous question also only apply for solutions?
No, because matter has a maximum amount of light energy it can absorb.
Does that mean like these people getting light from this constant would have a maximum like
Right.
this, so
Yep.
does that have any effect on the table? Or-
Yeah, it has an effect on the table.
Would that change that? How would it be so-
Slowly breaks it down. Light's energy. It has more energy than the table does, or else the table would be glowing. Right? So ultimately, it breaks it down. Obviously, the sunlight, this isn't the whole spectrum, right? The sun has the whole spectrum. If you leave a chair outside, what happens to your chair? You go a year later and it's brittle, right? Even though it just sat there, it's breaking down. Now, it would take a long time for the fluorescent lights because it's just a small part of the spectrum. Like long time as in way longer than 100 of your lifetimes, 1,000 of them probably. Does that make sense? But yeah, it is. It's all energy. It's all energy. What do we think about this? Pretty cool? Beer's Law. You don't have to memorize it. You'd be given Beer's Law. I recommend that because you'll be given it like this. So just remember you can remove that B. Right? You can remove that B. Pretty cool, huh? Oh, sorry. Pretty excited? Beer's Law? No? Stick with me. It's gonna come back. Because this was just sugar water, right? We just had some sucrose and some red dye and some citric acid. We didn't have much stuff in here, but as soon as we start adding different stuff, all kinds of cool stuff starts happening. Yes, sir.
You said that the absorbance does not depend on what the solution is, right?
What do you mean it doesn't depend? Yeah, it will change with the solution.
Oh, yeah, okay, never mind.
Okay. Yeah, this will be unique for, yes, that'll be unique for the solution. Okay, so keep this in the back burner because it's coming back. Keep that in your head, look at it. Try to remember it. It's not going anywhere, but let's get back to our workbook before your quiz. We are on page 189 of your workbook. 189 of your workbook. And how does this relate to Beer's Law? Molarity. We need to be able to find molarity. That's an important part of Beer's Law. So a lot of these questions are finding the molarity, different ways to find molarity. So here it's saying, what is the concentration? That is another name for molarity, right? So what's the molarity of this flask? What is the if this flask is used to make a solution with 38.25 grams of lithium phosphate. Where did that 3 come from? Where's that 3 come from? The charge on phosphate, right? The charge on phosphate. Phosphate is -3. So how many lithium atoms at +1 do we need? We need 3 +1s, right? So that's a quantity of how much lithium we need for that -3. Don't forget that. So molarity equals mole over liter, non-negotiable. They're showing me a picture of the flask that's 1,000 milliliters. So 1,000 milliliters, how many liters? 1 liter. Good. So 1 liter. It's asking for the big M, molarity. I need to find mole, and all they've given me is 38.25 grams of lithium phosphate. How do I go from grams to moles? I'm going to divide by the molar mass of lithium phosphate. Who wants to do molar mass? Abby? Yeah.
115.79
Grams per mole. And our grams cancel and we're left with mole. Grams per mole. Did everyone get that? Can everyone get that? Harris, you're not playing today. You don't play along. Okay, it's okay. You can have a day off. Okay. So when we do 3825 divided by 115.79, we get 0.3303, and that's moles. But it's asking for concentration. So what is that divided by 1 liter? Isn't it just that? Right? So 0.3303 molar is the concentration of the lithium phosphate. And ask what the concentration is. That is the concentration answer. Sound good? Yes. There are 4 sig figs right here. So there are 4 sig figs right here. The what? No, this is the name of a flask. And remember, these are way more precise than a balance ever would be. So the precision on this is not even like 7 or 8 or 9. We don't even want to go there for that precision. So you guys want to do another one? You want to try it by yourself or together? Together, okay. I got 15.8 grams of KCl. It tells me it's dissolved in 225 mils of water. And it's asking me to calculate the molarity. Molarity is mole over liter. And I need to convert both of these into the units I can use. Milliliters, how do I convert milliliters to liters? I move that decimal over 3, 1, 2, 3. So I'll have 0.225 liters. Everyone good at milliliters to liters? So in your quiz, tell me if you're good at milliliters to liters. Cool. And then to go from grams to moles, I'm dividing by the molar mass. Chlorine is 35.45. And potassium is 39.10. So I've got 15.8 divided by 74.55 grams per mole. My grams cancel, I'm left with mole. So I have 3 sig figs here. So 0.212 moles. I divide those numbers to get my concentration. So 0.212 divided by 0.225. 0.942 molar KCl. 3 sig figs. In my answer, I need that big old M for molarity KCl. So that's the molarity. Pretty straightforward, right? The next one, however, asks for mass. So you're always going to be given 2 and ask for the third. Molarity equals mole over liter. So to get mass, that's going to come from mole. So they better give us the molarity, and they do, 0.250 molar. And they give us the volume, 0.2500 liters. You need to solve for mole and then convert it to grams. What do I do with these two to solve for mole? Multiply them together, right? These two together give me mole. So 0.25 times 0.25. 0.0625 moles, but it's asking for mass. Luckily, it's KCl. We've already done the molar mass of KCl up here. So I'm just going to multiply that by 74.55 grams per mole. Mole cancels, and I'm left with grams. How many sig figs? 3, because this is 3 sig figs, because this was 3 sig figs. 4.66 grams of KCl. The next one's new. Can you solve for volume? To give us molarity, so 3 sig figs, 0.300 molar. We're trying to solve for how many liters. They don't give us mole because that would be too easy. They give us grams, so I need to go from grams to moles. Luckily, it's KCl, so 74.55 again. 6 divided by 74.55. 0.0805. Did I do that right? You don't know? Okay. Now, what do I do to these two to get my L? I don't multiply them. How do I get L? Mole divided by molarity, right? This divided by that. This divided by that. So this goes in the calculator first, 0.0805. Divided by 0.3. And I get 0.3 sig figs. 268 liters. Now, how many milliliters is that? Yep, 268 milliliters. And that's kind of a little more lab friendly. You could do that with a graduated cylinder. It's a lot more lab friendly than the this divided by that. Did I do that right? This divided by that.
Yeah.
Because that's not algebra. Okay. Okay. Sounds good, right? How do you feel? Good? You want to try it? Yes.
So if it's not specified, should default to answering in milliliters.
Oh, it's liters. Liters. Molarity is moles per liter. This you don't have to do that. That's just so you can picture it. It's a little more
Right,
lab
I'm saying,
friendly.
so that would be incorrect on both.
Calculate the volume. This would be incorrect on a quiz, yes. .268 meters. Yeah, that was just me adding what you guys did. So like half a water bottle, right? It's 500 milliliters. So about half a water bottle. Need you to start picturing this stuff in your head. Instead of it just being numbers, you need to picture it. Sound good? I need everyone to get out their laptops, please, and go to yeah. Oh, here's the pass. So. Today in class, you turned in your molarity. You will get back their checkup, homeworks from last class. I still see some over there, so make sure you pick it up. We got some notes on Beers Law. You don't need to remember. It's a much better picture than what I drew. And then we're taking the molarity quiz. It says here, when you're finished, students should read the following site. I highlighted this because maybe you couldn't tell that that was a link. Because even though you put in links, so when you finish, don't do nothing. There's this site on solubility, even though we're not going to that just yet, but it gives you something to read. Or you could go back to your workbook, but don't just sit there. Let's try to use our time a little better. And look at the name of this. It's called what?
Easy malaria.
Read the whole thing.
Number 1.
Number 1. So number 1 indicates, what do you think?
There'll be more.
There'll be a number 2. Yes, there will be a number 2. Difficult in any way. Don't forget, when you see this dot, it does not multiply, it's associated with, right? So you mass copper and sulfur and 4 oxygens and 5 waters. You add them all together to get your molar mass, right? That's called a hydrate. You guys remember that? It's been a couple months since we did that. Thank you for absolutely no feedback. I appreciate it. Absolutely not. That's okay. I taught last year and you guys were little black dots. Well, sometimes you were colored. One guy was this Kodiak bear, Cyrus. I remember him. They had this Kodiak bear staring right at me all the time. He never said a word, but very aggressive, snarling bear. Kodiak bear. Squidward. I had so many Squidwards. Right? Yeah. So the next thing on page 190 is something called molarity by dilution. This is the real life stuff. This is what you will use in real life if you stay in the sciences. It's what you'll use in AP Bio. It's what you'll use in AP Chem. It's what you'll use the rest of the year in here. It's called molarity by dilution. Couple things to remember. You can only dilute a concentrated solution. You can't make, well, I shouldn't say that because no, never mind. Molarity by dilution. It's used a bunch in real life. So here's real life. Me in a chemical storeroom. You can go in there, which you can't. You would see it's full of a bunch of shelves. The shelves have lips on it. They're called earthquake lips. And that's prevent bottles from knocking off the shelf during an earthquake. You'll notice everything is stored low. This is all kind of just fluff. And it all has to be stored below eye level. I know you're wondering about Miss Babcock. She's like this tall. I get you. But we don't let her in the storeroom. Anyone know why everything has to be stored below eye level? They can just explode. So, no.
So you can see it if you're trying to grab it.
No, really. The reason everything is below eye level is because they may explode. That's the answer.
Oh. I thought you were
So it's better that it's.
I thought you were just telling me I was wrong.
So if it explodes, explode over this. Right? Yes, sir.
You personally have been exploded on like.
Yes, absolutely. Absolutely. Without a doubt. Now, so I'm a teacher and I want to make a lab. Everything is labeled with its molarity and its ID. I need acid for you guys. I'm not gonna, this is a big jug. It's a 4-liter jug of hydrochloric acid, 8 molar. I can't bring that to you guys because I don't want you to die, right? So this is what's called a stock solution. Stock solution. I know the molarity because I can read it off the container. I know the molarity. That's a known thing. I'm going to pour an amount out of this jug into a graduated cylinder, which means I know the volume. Does that make sense to you guys? And then I'm thinking, well, I need them to use acid, but I don't want it so bad. I want to dilute it to a molarity. So I know another molarity. I want it to be 0.1 molar from our 8 molar. You with me? So this is known. This is known. You know, I want to keep you safe. I mean, it'll still hurt you, but it won't kill you. So the question is, what volume do I need? Now, these are my, I don't know. I don't know, right? How much do I need for class? Well, I got 156 students, and that's like 75 groups, and then some people might spill, and some people don't measure. Yeah, so I need to make 6 liters. That's a volume. So how much of this do I need for this? Does that make sense? This relationship, molarity by dilution, is very important, and it's very handy. Very handy. Do you understand what this is about? Now, the only thing that'll screw you up is what molarity goes with what volume. What molarity goes with what volume. And you get that from reading comprehension. Couple tricks with reading comprehension is of. If there's an of in between, they go together, right? Because of means multiply. Yes.
Also, one of the higher volume over the lower,
Nope.
since they're equal, right?
Nope. Doesn't work that way. Depends on where you're, would the higher volume go with the lower molarity and the lower volume go with the higher molarity? Is that what you're saying?
Yeah.
With straight up this, yes, but this relationship changes when we're talking acid base. But yes, you understand what's going on. You got it. So let's try one. A stock solution of 1 molar NaCl is available. It's a stock solution, so that's in the chemical storeroom. How many milliliters are needed to make 100 mils of 0.7500 molar? These two go together. This is a molarity and that is a volume. What's the question asking for? Milliliters, which is another volume, right? And it gives me another molarity. These two go together, right? So we're just going to plug and chug. I got a 1.000 molar solution. I'm going to solve for volume. Now, you do not have to convert to liters, but whatever goes in is what comes out. This is asking for milliliters and milliliters is going in. They just need to match. And we have 100 milliliters. 0.7500 molarity. Everyone cool on how to solve for V? I really hope so. What do you get? What? 0.0 milliliters? 75 milliliters. How many milliliters are needed to make 100 mils? Okay, so your volume, you should have gotten 75 And how many sig figs? Milliliters. Did everyone get that? Yeah? So what is that really saying? You had stock. It was 1 molar NaCl. Right? You're thinking in a lab, I need 100 mils. I need 100 mils. I need this whole thing full of 0.7500 molar NaCl. What you just found out is coming from the 1 molar stock. So you're going to pour out of here 75 mils of it, like up to here. Does that make sense to you guys? That's what you just found out. What do I put what's the rest of it? Water. The rest of it is your water. You're going to bring the total volume up to 100 to get your 100 mils of 0.75. See how that works? Molarity by dilution. It tells you exactly what to do, how to make the stock solution. Now, I want you all to imagine this to be one of those Kool-Aid bottles. Right? You'll be told the molarity. You're in control of how much you pour out of it. Right? So that's molarity and volume. I can ask for a molarity and you would have to make it. Does that make sense to you guys? And how would I check to see if you did it right? Colorimeter. I would just take a little squirt, stick it in a cuvette, stick it right in there, look up on the chart, and you either got it right or you got it wrong. You either did the molarity right or you didn't. So 100%, that is part of your lab practical. Molarity by dilution is part of your lab practical. And you're going to be doing it with the Kool-Aid. Sound good? And we test it with the calorimeter. Anyone have questions on that? Hey, new guy. We do lab practicals in here. What's your name again? Nicholas. Yes. Nicholas. And do you go by Nicholas or Nick or Nicholas? Got it. Sorry, I forgot. So I just called you new guy. Hi, Nicholas. How you doing? Yeah? Do you like lab practicals? Did you have lab practicals in your other high school? Okay. It's when you're going to go to the lab and I'll test you on it. Okay, cool. Want to do another one? Yes, yes, please, let's do another one. What volume of, see that word of? This is a V. So this goes with this molarity, is needed to make 100 mils of a 0.1 molar solution. So we're solving for V. We're given molarity. We have another volume and molar. Hundred times 0.1 divided by 0.25. If milliliters go in, milliliters come out. What do you get, Abby? Anyone doing it? 40.00 milliliters. Sound good? Making sense? Number 3 says concentrated, what's the name of this? So no hydro because this is polyatomic ion, right? So this is sulfate, but we ended in ic. sulfuric acid, right? Some people call it sulfuric acid, just because it sounds cooler. So concentrated sulfuric acid is 18 molar. If 0.112 liters of the concentrated solution is diluted to 2 liters, what is the molarity of the diluted solution? So what this is saying is they took concentrated solution. They have a big 2-liter graduated cylinder. This is H2SO4 and it's 18 molar. They pour in just the tiniest bit, just 112 milliliters. Right, they fill it up here with 112 milliliters. And then what's the rest of it? Water, right? So this little bit is the concentrated part that came out of the stock solution. The rest of this will be filled with water. So you could subtract to find out how much that is, right? How many milliliters of water. So then once it's all diluted and the volume's up to here, it's saying, okay, now what's the molarity? What's the molarity when you dilute it that much? I keep going back to this so you think about what's going on, because the questions are going to get harder and ask more about procedure base. So really kind of think about what it's talking about. So we got 18.0 molar. We've got a volume, 0.112 liters. We got another volume. So what is our second molarity? One. And that is still H2SO4. It's still H2SO4. So molarity has to have a subject. Molarity has to have a subject. What do you think of this stuff? Crazy hard? Not hard? Crazy easy? Not easy, not hard? For homework, you should at least do like 7 through 12. Yeah, you should at least get really good at these guys. And maybe finish this page, finish page 190, except for like 3 practice. Just to keep you on track. Of course, you do whatever you want, but
Please don't. Do the random page numbers
how'd you know it was him?
because I have my sources.
But I kept his confidence. You didn't get it from me.
Was it a Joey Burgess? No. Yeah, Joey Burgess on the idea to get the random page number. It's so annoying. I can't wait. I have my sources. 100% Joey Burgess. It was Joey.
Hey, you're listening to Joey.
Hey, Gray, you want to take pictures of these?